Yes. Well, relativistic speed is transformation of velocity observed by different observers. That is relative velocity. And although this idea it has been used since Galileo in physics, in Newton's mechanics before. And I remember that when students in year 11, they studied relative velocity formula from mathematics course. Have you done that? For example, the river, the boat is moving the river, and then the person observed on the riverbank will see the velocity different from the relative velocity to the water.
Yeah.
Right? So you know that idea. So that is a classical idea. So depending on how we can talk about that. So the velocity, relativistic velocity. So the key word is that they have two meanings. Relative, which means just relative velocity, right? Relative velocity. That simply means a relative velocity. Relative velocity. Another meaning is that when relative velocity, another meaning is a relative velocity at velocity and at high speed. Okay, high speed. It's different idea. So maybe not high speed, just relative to speed of light. This is a relativity, velocity, sorry. Velocity. That is a velocity. Rewrite these two words. So depending on, let's write down first, velocity. The velocity. One is say the velocity over c approach to 0. Okay. And then the velocity, another is velocity approach to c. Okay.
Yeah.
So if depending on what you, of course, if you ask me this question, I understand you are actually focused on this scenario when the velocity is close to the speed of light speed, right? Now in this case, unfortunately, and normally you can find the formula in the Einstein special relativity. But I wonder, do you think your textbook will teach you this transformation? So basically, you are going to transform. So last time we're talking about the transformation. Last time we talked about Lorentz transformation first. That's something I don't think you will learn. One is a Lorentz. By the way, in this case, I write down here. In this case, they use Galileo transformation. Galileo transformation. Transformation. And in this case, we can use a Lorentz transformation. Now, if you know the transformation, we can easily answer this question. So basically, we can answer this question. If the velocity relative for the, I use this notation. If the velocity dx dt is known, how can we transform that into velocity, which is dx prime and dt prime? So that is the question. Do you agree? Yeah. Are you sure you are going to study this subject? If so, I have to show you how to got this.
Oh, it's formula. Relativistic momentum.
Not velocity.
No, momentum.
Yeah. Momentum is, well, by the way, momentum is also the product, you see.
Mhm.
We just, but before that, can we just write this formula? So this is a form. So if the object, can you see this object is moving? This is C, right?
Mhm.
And it is moving. We know this object moving. But for this object in this frame, so this is called X prime frame. And he would consider his velocity is at dx prime, dt prime, right?
Yeah.
But for the observer, can you see this is B, this is A. For the observer in a different frame, and he would measure that velocity of this particle C is dx and dt. So it's not straightforward in relativity, okay? Because in this case you have to that's why I need to know how far you want to go, because for Lorentz transformation we have the, do you remember that transformation? Last time we have obtained this transformation. I just recall that 1 is negative v over c squared, this negative v. Okay, so that is transformation for x and t, all right? So you have to work out this transform. In principle, you can depend on the Lorentz transformation to work out this one. By defining, can you see, if we just rewrite this part, we know x prime is equal to gamma 1 minus, right? Not 1 minus, x minus, sorry, equal to x minus vt, right? And t prime is equal to gamma. And if you follow this one, just use for t, that's minus v c squared x. Okay, so this so what we can do if you want to know that we can do the first derivative. Can you see? The first derivative, but this time you have to find the dx dt first. So dx prime is equal to dx take v dt, right? And the dt prime is equal to gamma dt minus vc dx, right? So if you therefore you can work out this first derivative, the velocity relative to observer B, dx t prime. Can you see? You just divide it. Can we? Can you follow me? So just dx minus v dt, right? Divided. It's just algebra. You can do it. Okay. That is based on assumption. You will learn the Lorentz transformation. If you don't know, if you haven't learned Lorentz transformation at school, I don't think this piece of knowledge is required. You see?
Yeah.
Anyway, we have go that far. Can we just divide? Can we simplify? Can we divide the dt? Divide the dt, can we? So that became dx dt. Can you see? Take and v, right?
Yeah.
How about this part? That would be 1 take v, this is c squared, sorry. You see? That is c squared and dx dt. You see? So we found this relativity already. Can you see? So this one, this is the formula you want to know. If we know this one, we should be able to work out the momentum. So this is one velocity. That is another one. Can you see? So if you wish, can we just denote this velocity? Can we just call this this velocity? Can you see? To make the velocity different from this relative velocity between the frame, can we use a capital letter? Can we use a capital letter? Let's can we call this as a Vx? Just called V, right? Can you call it V prime? I use capital letter. So according to this formula, so this formula can be simply written as right to this corner. this is dx dt prime is just v prime. Can you see? Can be written as v minus capital V. I use the capital V. Can you see? Take the small v. Small v is relative velocity between the two frames, right?
Mhm.
And divided. So that's different from Galileo's. Divided by this. Can you put it as a v? And the capital V divided by c squared. So we got it. So that is a transformation of velocity. I can write the formula here. So relative velocity relative to the frame B is equal to velocity relative to A. Take the relative velocity between two frames and divided by 1, take V, the small v, multiply the big V, and divided by c squared. Yeah, so that is based on the Lorentz transformation. Do you agree?
Mhm.
I think your brother studied this. I told your brother as well. So basically, if you want to know this transformation, then this is formula for how to transform the velocity, which is different from a Galileo's velocity, right?
Yeah.
The Galileo's velocity transformation doesn't have this part, so it doesn't have this factor here. Can you see?
Mhm.
Obviously,
Yeah.
this factor will become 1 if the velocity is lower, much lower than the speed of the light. So basically, you can argue that this formula will return to the classical form, which would be v prime equal to v minus velocity. Can you see?
Mhm.
So when the v over c is approaching to 0. Can you follow me? So this is when you answer this relative velocity, you have to consider which frame they used, where is observer.
Mhm.
Now your question is a little bit undefined. Your question is asked the relativistic momentum, right?
Yeah.
Okay.
We'll start studying it next week.
Relativistic momentum, yes. So in this case, we have to. So what is you have two. So this is can we do it one side by side? We do comparison. So another is classical, right? Galileo, classic. They just Newtonian. Okay. And just say Newtonian. Newtonian. Do you know the definition in mechanics? P. What is momentum? So the object is moving.
Oh, mv.
V, yeah. Can we use capital V? So that is the mass multiplies V. Yeah, that's it. But eventually, this is mass, it's main. This is the classical physics. But before that, probably you have to learn that in the relativistic relativity, in Einstein's relativity. In the first place, that mass is no longer constant. Maybe you will need to learn this formula first. Mass will equal to mass gamma. You know the gamma factor? Yeah. Multiply the mass 0. So this is a basic Einstein formula, right? We don't have to prove that. So basically, this mass is called the rest mass. So in Einstein's idea, the mass became variable. They became velocity dependent variable. This is called rest mass. So this is a new idea, rest mass. Okay. Do you remember gamma? Do you remember the gamma factor? It's gamma factor, right? 1 take v squared divided c squared. So therefore, if you substitute this formula here, then we can get the momentum mass can be written as mass at rest, okay, divided by the one take the relative velocity v squared divided by c squared. So before you cannot use this mass anymore. Can you see this is according to Einstein, this is the rest mass. Can you see? So from here you can see the formula for the momentum is different. Can you see that? So what in other words, in relativistic formula for the momentum, so therefore you can conclude that the momentum in a relativity or relativistic form can be written as m0 v divided by square root 1 take v squared and c squared. Now I have changed. Here we have assumed that a small v equal to capital V, right? So basically, in this case, what we are doing that, so we know that if you just using the frame, which is observation take place by B, right? So this frame is not moving. This is X, right? So the another frame is actually moving. So this object is actually moving with another frame. You can draw that. So for example, this object could be you can draw this frame here. Can you see? So you can see that object is moving together with this frame. Can you see? Okay. So in this case, and so the velocity of, so basically the relative velocity, how to say, in this case, let's just use purple color. So that is the case, it's X prime, can you see? So this time the object is fixed on this frame, all right? So therefore, the velocity, can we call this a B? Can we call this object C, right? And this moving is a B, and this not moving frame is A, right? So the velocity C relative to B is equal to 0. Therefore, right? So VC is equal to VB. By our notation, this VC is capital V, and this VB is a small v, right? That is why what you're going to learn is this formula. Little bit indirect, can you see? So this is formula you need to learn. So next time when you are asked to calculate the momentum of a moving object, then you have to ask what is rest mass, okay? And then you have to, of course, you have to follow the definition. You have to say what is the velocity. Can you see this the difference between these two formulas for momentum? Newtonian and relativistic formula are different.
Yeah.
However, if this factor, if gamma factor approach to 0, you see, so they are related. Asymptote, right? Do you see the asymptote? It's asymptote form of this so as the gamma approach to 1, can you see? Or in other words, velocity over c is approach to 0. So these two different formulas are related.
Yeah.
Any question? So the difference is due to the mass. The mass became velocity dependent. That is the issue.
Okay. And so the momentum would change depending on who's watching.
No, in this case, when we discuss the momentum of object, we will just focus on, no, they just, only one is, sorry, this is not A, this is A, observer A, right? He used his clock to start to measure the velocity. Okay.
Yeah.
Because relative to this person, he's not moving. So this object is not moving. Therefore, the momentum is equal to 0. Can you see? You understand?
Yeah.
So because this object is moving together with this object, so therefore the relative to this observer B, the object is not moving. If you want to know the, of course, if this is assumption, if this the issue will become more complicated if you just consider that there is a 2 frame of reference like this one. Can you see? And there's one object is moving, right?
Yeah.
In this case, and you have to use a relative velocity. In that case, the formula will be different. Can we use a capital? Well, can we still use capital letter to represent the V, right? And then the form. This is a good question. For the observer A, the moving object with mass, rest mass m0, and according to him, can you see, the momentum is simply equal to gamma, or have to specify what gamma is. It's simply equal to m0 divided by square root. Oh, it's a bit crowded here. Let's just write down here. So P is equal to m0 divided by square root. 1 take V, okay? Small v, that is relative velocity, all right? Relative velocity. And that is a c square, can you see? However, relative to this guy, can we just use a p prime? Because in this case, the relative velocity is just the velocity of the v. And this formula will be, oh, I forgot about the v here. This is capital V. So in this case, and these v are the same, can you see? I don't think you will go that detail, but I just show you they are slightly different. Can you see? These two formulas are slightly different. So in this case, you have to specify which is frame A, so this is frame A, this is frame B, right? Otherwise, the moment, oh, today we have, this is more than enough. Okay, we have the formula for transformation of velocity observed at different frames of reference. Secondly, we also work out the relativistic formula for momentum. I think that is what you're going to learn.
Yeah.
If you want to know more, I can. Any question? Do you find this of the mass change? Do you want to know why the mass changed?
Yeah.
Yes.
Why is relativistic momentum important?
No, this is not important if the velocity is if the object is moving at a much lower speed than c, right? It became important because that is required by Einstein's formula, relativity. So from now on, you will encounter 2 types of the description. One is relativistic description, meaning we are going to describe the motion by using relativity, special relativity, right? Another is the Newtonian momentum, in which we will just use the original definition of momentum. Mass will be the constant. Because this is all related to the so why the mass change? Do you want to know? So this formula is really very important, because based on this formula, then we can work out Einstein can develop his formula for the energy. This is then you can imagine. But do you remember have you studied length contraction? If you have studied.
Yes.
Yeah. So what is about? Can you tell me what is the length contraction all about?
Like the distance changes because when time dilates, then the length also has to change.
Length will change. So the length changes. That's but the material is the same, right?
Mm-hmm.
So if the length change, what would happen? The can we just if I can use this simple idea to show you. Otherwise, we have to use more complicated. Can we just consider this is an object, right?
Mm-hmm.
And if the object is not moving, and that is the length, but when object is moving, they were contraction, you see?
Yeah.
So according to relativity, so they, oh, sorry. You can imagine that. So basically the, can we use the density to solve this puzzle? So this is original length, right? What's it called? A proper length, right?
Mm-hmm.
Have you heard of proper length?
Yes.
It's called a proper length. Now this is a length when the object is moving, okay?
Mm-hmm.
So again, this is observer A, for example, right? And he's not moving. So the object is moving relative to this observer A, right?
Mm-hmm.
According to the Einstein, time dilation will occur. If time dilation occurs, the length contraction will also occur at the same time. So the length and clock are related. Can you see?
Mm-hmm.
So this is X. So this object is moving. So this object is moving at a certain velocity. All right.
Yeah.
Do you know the length contraction formula? So what is length contraction formula? Can you tell me? We know the time dilation.
Yeah. It was, I don't remember it.
Something to do with the gamma.
Is it just gamma?
Can you just write the time dilation first? Then you can. What is the formula for time? Because these are two basic formula when you study this chapter. So one is, can we write down here? It's called the time dilation. Time dilation. In which the formula, in which they got proper time, you see? So the time here is, they have proper time is relative, the observer is not, clock is not moving, called the proper time. I read time dilation first. Time relative to the time, proper time can be written as this formula. Do you remember?
Yeah.
Okay. So can you just do you have the can you check your textbook? I don't want to go too far if you haven't studied much of the Einstein's relativity.
We did do length contraction. I just don't remember the formula.
Yeah, what's the formula? Length contraction? Yes. Yeah, today we will discuss the momentum, relativistic momentum. And we haven't just next time we'll study the energy, Einstein's famous formula for energy. So what is the relation between the length of a moving object relative to the length is relatively not moving, relative observer is not moving. So that is a proper length. So this is a proper length. This is called the proper time. For the proper time. No, it's different. It's opposite. It's different from the from length contraction. Similar but different. Yeah. You remember the gamma should be here.
Yeah.
Okay. Oh, well, can you write the full formula now? Can you, based on this, can you rewrite this formula as relation between proper length and the moving object, the length of moving object in another direction.
Oh,
yeah.
Is that?
Yeah, that's right. Yeah,
That's
right. So that's I can write here to compare. So this is L no square root 1 minus v square over c square. All right. So this is these are two basic phenomena in special relativity. I'm trying to figure out how to explain. Otherwise, we have accepted this idea that the mass is a change is relative to the yes. I noticed that sometimes equivalent of mass. Yes, there's some okay. There's some simple explanation, but not necessarily accurate. So they are trying to explain this formula that mass is velocity dependent. Can you see? They're trying to explain this formula by use contraction. Let's see if you can follow me. So basically, they argue that they work out this contraction by they work out the energy formula directly. That's right. So what is it? What's the argument? Let's just follow their idea. So the velocity, assuming that a box is very massive, the Combined coin speed is small compared with speed of light of momentum, which gives mv equal to E divided by C. No, I don't think this is a sum. This is not a pair. They have assumption in order to obtain that. Mass now multiply air and the air. It is not apparent, right? So we have to, it's not required either. So can we just accept this formula for mass? And we just use this formula to discuss momentum. Do you agree? There's no point to prove every formula, right? Because why don't we, one moment. I found the text. Do you have textbook? If you don't, I can find textbook for you. I see what you are really required. Do you have the digital book of your physics?
Yeah.
Yes. Why don't you have a look? Because I'm using a university level textbook. I don't think it's fair for you to learn that. I give you the green light. Can you share your textbook? We will read what is required for this momentum, relativistic momentum. The book I used before, they just teach students what is AHA. Relativity momentum, yes. Okay. Can you enlarge this part? I'm trying to say. They use Newton's law. Can it's too small for you to read. One moment.原来你有新的物理书买的没有？我还没拿上。今天好的，今天啊，好的，我去接的。 Okay, I couldn't find the textbook. Anyway, can we return to that part? It's very small to read.
Yeah.
Why don't you you use a screensaver, print screen of these two pages, this page and these two pages, that's all. This one and this one, you see? Can you print can you print these two pages and send it to me by picture, as a picture?
Like through email?
Yeah, you can email to me, yeah. Yeah, it would appear this time they ask a student to understand some more formula than before. Yeah, the screen is small. What I'm going to do. Okay. So can you stop your sign? I will check my email. Share screen. Go to email. Good. Download. Okay. Oh, good. All right. So they use impulse. That's the definition of this classical. Yeah, they're starting from classical or Newtonian momentum. That is that impulse law. Then they rewrite the second law of Newton into this form. That is impulse. That's impulse theorem. Can you see? This impulse momentum theory, the F multiplied delta t. So what they're trying to do? And they change the time. Okay, so this time is a proper time, the t0. Oh, they incorporate the gamma in this case. I see. Can you see? Can you see? Yeah. Can you see my screen? So basically, this delta t, the t is a proper time. Then they use the time dilatation formula to rewrite the delta t. Can you see? So the Newton's law changed to this form. Aha. So that is how they, oh, this is much simpler than my method. Can you see? They just argue that the time dilatation, not the length contraction, right? Because of time dilatation, we have replaced this delta t by delta t null by replace delta t null by delta t. Okay, that is the argument here. So you in here you have to get familiar. You have familiar with. Let's just annotate this part. Let's annotate. Can I write down now? No. Okay. I can't write anything. Oh, I can write now. Yes. So this is count. Do you know this is Newton's law? F equal to m delta v delta t, right? And they argue that at the beginning, we are starting the object is not moving. So the observer is not moving. The object is not moving. So in this case, they put the 0 here. So that's how they rewrite this form as we put 0 here first, right? So from this one, and they just multiply delta t on both sides, right? Yeah. You get m null, you get this formula. Can you see? That's how they get this formula. Delta v. So then that is a time dilation formula. So time dilation formula can either written as T equal to T null divided by gamma. Or you can just simply use delta. If you use a delta on both sides, that will become delta T equal to delta T null. Okay, if we just write a gamma factor here. So that's why that is, I think this very interesting, this very good way, because it's simple. They just assume they use the time dilation formula to obtain this form of the momentum, because from here you can, if you go further, that will become gamma m null, okay, and become delta V. So if I stop here for a while and go back. So that is how they obtain this formula. So they argue that delta V will equal to this. Now, for some people, this is not apparent because you see the gamma involves the velocity. Can you see that is you just, I suggest just accept this result, right?
Yeah.
And because if you want to know more, then you have to define what is a gamma is, right? Because this as I say, that we prefer to use a capital V. For gamma V, we use a small v, right? Small v squared c squared. But anyway, that is that's very convincing. So basically, in this way, we can, from this one, we can obtain the form of momentum. Okay. So that is how the textbook demonstrate this relativistic momentum. And it's just clear that for. Yeah, sometimes you can look at the reference textbook to see what is required. So that is how they introduce the formula. Okay.
Yeah.
And there's another formula, velocity. If the velocity is needed, the mass and the relativistic increase in momentum are known. The formula PV can be rearranged to solve this one. So they solve the velocity, right? They solve the velocity. Now here they just assume these are the same, right? So this gamma, obviously gamma, they contain the same velocity. If you wish, you can look at this, how they actually. So basically, this formula, the original formula is this. The gamma, so m null is constant. They got v here, and this is 1 take minus v squared plus c squared. All right. Let's go to the whiteboard. You can try this one because it's opportunity to practice your algebra. So that is this for students. They take this simple deviation. They say, a moment. They say the velocity, the formula for momentum is m null multiplied v, right? Divided by 1 take v squared and c squared. Okay, can we find the formula for v? Can we solve this one? Do you want to try? Little bit algebra. You divided something. Okay, but this not yet. The velocity is on in the gamma factor as well. It's not simple.
Yeah.
So you have to try to work out the single a single formula. Haha. There's no shortcut. You yes. If you use this formula, so what is m? What is m in your formula? What is m?
Oh.
When you study relativity, you have to specify what is n, what is m null, right?
Oh, so it would be m naught.
Well, if it's m null, you cannot use the formula. This classical formula, it's Newtonian formula. So these two formula are classical or Newtonians. Yeah, Newtonian. So we have to return to this formula. You see, we have to, based on this formula, these two formula are not allowed because they are not they are incorrect in special relativity. These two formula are incorrect. Do you want to try again? How can we solve these puzzles? Given this is a formula, given this formula, how can we solve the formulas of V? Yeah, I think it's good. This is good because they use algebra. You have to use algebra. Good idea. Yeah, you square them first. Yeah. Aha. Let's see. Plus, right? It's a sum. It's a sum. Yes. That's the formula your textbook show. Yes. So that is a little bit of algebra. Okay. That's very interesting. We can return to the textbook. Okay, so that is, this is some diagram. Do you want to look at this diagram? What does this diagram mean? Can you look at this diagram? We got 3.0. That is represent velocity in this huge number, right? Velocity multiplied 10 to the power of 8. So the vertical line, can you tell me whether is a light speed in this diagram?
The blue line.
The blue vertical, right? At 3, very close to 3. The 2.99 is very close to 3. So can you tell me what is it? Why do they draw this diagram? So what is this purple colored line?
Classical momentum. So it's
Which is proportional, say linear equation, right? Proportional. But what happened to that green colored line curve?
it's exponential.
It's not exponential. It just represents the relativistic momentum. It's very strange when the velocity approach to the light speed, the momentum will become infinity.
Yeah.
So that is why this implies that no object can move as fast as light speed. If that were case, then the momentum will become infinity. So there's always have some infinity result. So that will be considered as this infinity or divergency is considered as something impossible or not acceptable in physics, right? So that is why this is another demonstration that the momentum cannot move that fast. Or another way, the direct way, can you work out this one? So what would happen? Oh, these two are consistent. If you look at this formula for the velocity you just obtained, what would be the velocity when the momentum became infinity?
3 times 10 to the power of 8.
Is that clear?
It would be C.
It would be C?
Yeah, or like close to C.
Yeah, how can we just rearrange that one? This is a little bit of mathematics you can learn, all right? Can we just put this p square inside? Can you see? And inside this square root, can we? Can we do that? Yeah. Oh, you got to see. You see the velocity is a C, right? Did you see that?
Yeah.
How did you know? Without using formula,
it can't ever be more than C.
More than C? Well, you will see. This is a very good chance. Maybe can we talk? We use the whiteboard. This is very important algebra we can, or physics as well. If I use this, yeah, this is something very interesting. So if we can use the same page. So basically, that is a velocity formula here, right? And so this is your formula, right? I just highlight your formula first. Okay. So my question is, what would be the velocity? So what would be the velocity at the limit when p approach to infinity? And can you work out this? This just I just created some mathematical problem for you. Can you see? Given this formula, what would be the infinity of velocity when momentum approach to infinity? Did you say C? I'm very interested to know. How did you know? How did you know it's a C?
Well, it can't ever be faster than the speed of light.
No, you can make. You have used mathematics. You have proved that. You maybe you are right, but in this case, as a physicist, you have to use mathematical. You have to do it. You have to show it mathematically. Have you studied limit when you study the calculus? Can you see that? For example, there was that x squared divided by 1 take x cubed, right? So what would be the limit? What would be the limit when x approaches to infinity? Have you seen this type of question in math?
Not really, no.
Oh, you should know. Yes, you should. This should be taught in before the calculus or as a part of introduction.
We did the first principle, but then we didn't go much into it.
I see.
And I don't remember the first principle.
Well, doesn't matter. We can take this as an example. Obviously, this we know that we know that with no the reason this limit is is related to the diagram. When with the do you remember the diagram? So that forget the color. So this is a light speed, right?
Yeah.
And that is this purple one represents a classical formula, dependence of velocity, right? So if I just redraw that, so this is velocity, but in a large number. So this is 3. So this is 0. This 1, 2, 3. This is multiply 10 to power 8 meter per second. Okay. So obviously this is a classical formula. M equal to V equal to M naught multiply V, right? But for the relativistic formula, and we saw that it's moving like this. Can you see? First is similar, right? As the speed increase, they become apparent different, and eventually approach to infinity, right? So this is that very useful diagram. Okay, can we return to this question? Can you prove that? Can you show? Can you find the limit? Which might be the C. Okay, you probably you are. This is based on intuition. Sometimes intuition works. Yeah.
It would never properly be C, maybe, but it's approaching C. It's getting very close.
How to prove that? Can we just write the formula here? We are looking for this limit, P approach to infinity, and we got this square root, P squared divided by M naught square plus P squared divided by C square. And this is a square root.
How do we do that?
Yeah, mathematically, how do we do that? Yes.
I'm not sure.
Well, you can divide. Can we just divide that P square? Can we divide P square? So this P square divided by P square, and also everything, the denominator also divided by P square. Can we do that? So that is divided by P square. Okay, can we simplify this? So you need to work out this result. You need to find the formula to convince readers. That is why the numerator become unit. Yes. Okay. How about second term? P is fourth. Are you sure? Wait a moment. Yeah. You'll be Einstein now. You'll have 1 inch away from Einstein.
No. Shouldn't it? Because it would be.
Yeah, that's why I'm not surprising. Some students getting confused. Can we just write down here M naught square?
It would be just C squared.
Yes, that's right. Divided by P square. Okay. Yes. Okay. That's right. That's constant. C is constant, right? Now, it's simple now. When as the P increase, what would happen to this term?
It would decrease.
It's not quite right. Double check. This is not right. You see, you really have to work out this first. Can you see? Can we just work out this, simplify this fraction? So this term is right. This term is not right. This is wrong. Can you try from here? Can you divide each term by P squared?
So it's me. Squared over P squared.
That's correct. Yes.
Oh, would it be 1 over C squared?
Correct. This time is correct. Yes. Okay, what would happen to the what would happen when p became not, very not, or even infinity? What would happen to the first term?
It would get really small.
Vanish, zero.
Yeah.
If not vanish, you can continue increase p, right?
Yeah.
Until it's vanished, until people convinced it's vanished. Okay, finally, that you will get the result based on this fact. So this what is the final result? Can you guess? 1 over and 1 over. No. Oh, this term is correct. Yeah. Okay, finally, probably. So this is something interesting. Is a p, that is p, sorry. Can we just copy that? Oops.
So it would just be c squared to the power of squared.
Yes, you nearly get that. If you substitute this correct answer here, so what can we just forget about this one? If you substitute this correct answer, what would be the final result? What would be the final result? Correct.
So equals c.
You are right. You're Einstein now. Okay. You understand? So you have intuition, and then you use algebra. You have proven that, right?
Yeah.
All right. I hope you were you can understand this relativistic form now, right?
Yeah.
Okay. I'll see you next week.
Yeah. Okay.
Okay.
Thank you.
You are welcome. Goodbye.
Bye.